Yeah, welcome to a massive open online course on fluid flow operations. Hello everybody. Yeah, we have in the previous class discussed about the fluid properties, and in this lecture we will discuss about the fluid statics, how the fluid will exert the pressure on the surface of the solid whenever it will be in rest, even if will be accelerated with uniform velocity, and then how it will act or how it will give a force to the surface of the body. So, in this case this fluid statics is generally concerned with the balance of the forces which stabilize the fluid whenever it will be in rest. In the course of liquid, you will see some pressure, there will be change according to its height, and it will be necessary to take its depth whenever it will be considered for measuring how much actually pressure will exert by this fluid on the surface of the body, which is immersed in the fluid, or the force will be exerting on the bottom surface of a container in which it will be kept. So, in this case whenever fluid will be statics in motion, statics in condition, that means that will be in rest in condition. So, in that case there will be no relative motion of course between the fluid particles, and that is why we can consider that the fluid will no have any shear stress in this condition, and the only stress will be involved in the fluid statics is the normal stress, and which is called pressure. And you will see there are two types of pressure will be exerting on the surface of the solid, and one is called uniform pressure, another is called non-uniform pressure. In case of uniform pressure, you will see if a uniform pressure acts on a flat plate of a area considering A here, as per this diagram. In this diagram whose area is A and a force P pushes the plate, then one can write that P will be equal to F by A. What is P? P is denoting denoted by pressure, and or F is called force which is exerted on the plate surface, and in case P is the pressure and P is the pressure force. Here in this case P is the pressure and F is the pressure force. Here not capital P, it is F is the pressure force. And for non-uniform pressure, if the pressure is not uniform, you can say that pressure acting on the minute area which is represented by delta A, and it will be expressed by the following equation here, that is small p will be equals to limit of delta A tends to 0 delta p upon delta A. Here it will be actually delta F upon delta A instead of delta P. Here F is pressure force and small p is called pressure. So, it will be represented by dP dF by dA. So, we are having that uniform pressure, if a uniform pressure acts on a flat plate of area A and a force F pushes the plate, then one can write P is equal to F by A. In this case P is the pressure and F is the pressure force. For non-uniform pressure, if the pressure is not uniform, then the pressure acting on the small area delta A which will be expressed by this dF by dA. Now, what is the unit of pressure? Generally, Pascal is the unit of pressure which is widely considered, and it is also expressed in bars or meters of water column, that is in millimeter of water column. And in some cases atmospheric pressure is used, that is called 1 atmosphere with the reference pressure, and 1 atmosphere is the standard 1 atmospheric pressure in meteorology and is called the standard atmospheric pressure. 1 atmosphere will be equals to 760 millimeter mercury at 273.15 Kelvin, whereas G will be equal to 9.80665 meter per second square. G is called gravitational acceleration, and this atmospheric pressure, that is 1 atmospheric pressure, will be equal to 101325 Pascal. So, in this table here see one relationship between the different form of that is different type of units or different forms of units to express the pressure is given here. Like Pascal is 1 Pascal is equal to 1 Newton per meter square, and 1 bar will be equals to 0.1 mega Pascal, and water column meter is 1 unit, that is millimeter water is considered, and then it will be equal to 9806.65 Pascal 1 millimeter mercury equivalent to here. And in this way, from this table you can calculate what should be the pressure. Even pressure also can be expressed in terms of unit torr, that is torr, 1 torr equals to 1 millimeter mercury. Now, absolute pressure and gas pressure is the two another important form of pressures here. See, generally two methods to express this pressure. One is based on the perfect vacuum, and it is called the absolute pressure, and based on the atmospheric pressure it is called the gauge pressure. Gauge pressure is equal to absolute pressure minus atmospheric pressure, and a pressure under 1 atmospheric pressure is expressed as a negative pressure, which is called vacuum, and 1 standard atmospheric pressure at 40 degree latitude at sea level, it is considered for the standard atmospheric condition, that is here absolute standard atmosphere, it is considered as at 40 degree latitude at sea level. And the standard atmospheric pressure, that is 101.3 kPa, it is considered, and 14.7 psi, 13 inch mercury, 760 millimeter mercury, 1.013 bar, and 34 feet of water. This is the different that is unit, or this is the different form of expressing the pressure. So, all are like this. This is the standard pressure or standard atmospheric pressure, you can say. So, this is 101.3 kPa is the standard atmospheric pressure, and that will be of course considered at the sea level of 40 degree latitude. Here see one example of the pressure. A pressure can be measured to be a vacuum of 23 is measured to be a vacuum of 23 kilopascal at a location where the elevation is 3000 meter. Then what should be the absolute pressure here? So, here P atmosphere at 3000 meter elevation is 70.6 kPa. So, then P absolute will be equals to P atmosphere plus that is P, then it will be, that is P is vacuum pressure is 23 kPa. So, it will be 76.6 minus 23, then it will be equals to 47.6 kPa. And here in this diagram, see from the sea level, here it will be 1 atmospheric pressure, and here the barometer reading like this, here this in this from this 1 atmospheric pressure. Above this atmospheric pressure, this is called gas pressure, and below this atmospheric pressure, it is called the vacuum pressure, and then this up to this, it will be called as absolute pressure, and then what should be that absolute pressure. So, from the simple relationship of this, gas pressure will be equal to absolute pressure minus atmospheric pressure, or you can say that absolute pressure will be equal to gas pressure plus atmospheric pressure. So, absolute pressure will be equal to here, what should be the absolute pressure in this case? From the sea level you have to add atmospheric 1 atmospheric pressure with the gas pressure, then you can have the absolute pressure there. Now, let us consider that what will be the characteristics of the pressure. The main 3 characteristics of the pressure is first of all, the pressure of a fluid will always acts perpendicular to the wall in contact with the fluid. Here see the diagram for the liquid, whenever it will be kept in a what is that, in a liquid column, you will see from the bottom to top how pressure will be acting on this surface of the column of this container, and in this case at the bottom the pressure will be higher. So, you can get that high pressure water jet from bottom, whereas in the middle section you will see there will be a relatively low pressure, that is why low pressure, relatively low pressure water jet, and from the top here there will be a very less pressure. Now, that low pressure water jet you can obtain, the water is coming from the nozzle, that is why you are getting the water from the nozzle as a jet. So, this jet force will be more at the bottom, whereas at the top it will be relatively low. So, it depends on the height of the column of liquid in the container. Now, pressure of water increases with the depth. So, we can say that the main one of the main important characteristics that the fluid always acts perpendicular to the wall in contact with the fluid, and it will be related it will relate to the height of the liquid column. Here again, in case of gas, you will see if you force on this container, suppose this container contains the gas, and if you apply the force from the top of this container, and you will see, since the gas is compressible fluid, then it will go downward, but pressure inside that container will be higher. So, in that case, if you are increasing the force there, you can get more pressure. Now, another important characteristic is that the pressure value which will be acting at any point in a fluid at rest will be equal to will be equal and in all directions on all directions whenever it will be exerting in a particular point. So, the values of the pressure acting at any point in a fluid at rest are equal regardless of its direction. See the diagram here. One, suppose this is one container, here this is called triangular prism. Here some liquids is are there. So, how pressure acting on a minute triangular prism there. So, in this case, if we draw a free diagram of this that is triangular prism, then we can say what are the force acting on this surfaces of this prism. So, in this from this bottom there will be a force like this P y into dx dz, and in this case P x into dy dz, because P this is in x direction, what will be the pressure, that is P x, in the y direction the pressure is P y. So, in the x direction what should be the force acting on this surface, in this surface in the x direction it will be P x into dy dz, P x into dy dz, whereas in the y direction the force will be P y into dx dz. Dx and dz is called the minute area, and here dy and dz is also minute area in the x direction. So, and another force, if it is acting in this surface of the fluid perpendicular to this surface of the fluid surface, then you will see the pressure is P into force is to P into dx ds into dx. What is that? Ds is nothing but the small area of the surface of the liquid. So, in this case total force will be P into ds into dx. So, if we consider the force balance in x and y direction, we can say that summation of f x will be equals to m into a x. Then if we substitute this force, then p x into dy dz minus p into ds dz into sin beta. What is that? Beta is the inclination angle here, beta of the surface of the prism with the horizontal surface. So, here beta. So, what should be the force acting in the x direction for this? So, it will be p into ds dz here. If we consider that, then it will be acting like this. It will be in the y direction, it will be in this direction. So, it will be minus, because here from the bottom the force will be equal to p u I into dx dz. So, it will be in the x direct positive y direction, and in the negative y direction it will be equal to p ds dx into sin beta. So, that will be equal to what should be the acceleration in the x direction. So, it will be rho into dx dy dz by 2 into a x, that means rho into volume, average volume, or that is total the volume of this prism, then it will be rho into volume, that means you have to mass into acceleration in the x direction, so it will be force. So, in the x direction force balance will be this, and in y direction it will be again total sum of force will be equals to m into a y. A y is the acceleration in the y direction, then it will be what is that? In the y direction it will be what this p y dx dz minus p into ds dx dz cos beta minus rho z into dx dy dz by 2, that will be equals to here rho into dx dy dz by 2. So, here it will be in the y direction, here in the y direction, earlier that will be your x direction. So, x directional force balance, it will be here in the x direction p x dy dz minus here it will be acting in this direction, in the x direction it will be in the x direction, and whereas in the y direction this force balance, this one and this one, this and this, whereas in the x direction this and this direction. So, from this two force balance, if we consider this from the geometry, also we can have dy is equal to ds into sin beta and dx will be equal to ds into cos beta. So, from this geometry and along with this force balance, you can simply have this p x minus p is equal to rho into dx by 2 into a x, and in the y direction it will be p y minus p into rho into dy by 2 into a y plus g. So, from these two equations, if we compare equation 5 and 6, you can say that p x will be equals to p y, and that will be equal to p, and p x is equal to p z, that will be equal to again p. So, overall we can say that in the p x will be equals to p y equals to p z, that will be equals to p. So, in all directions the pressure acting will be equal to each other. So, the third characteristics of the pressure is that the fluid pressure applied to a fluid in a closed vessel is transmitted to all parts of the same pressure value as that applied in the fluid. So, when the small piston of area A, area A1 is acted upon by the force F1 here, the liquid pressure P will be F1 by A1, that means force per unit area. Similarly, you can say that the same pressure will be acting on this cross sectional area of this piston, and in this case it will be P is equal to again F2 by A2. So, if we equate these two pressure, then you can have this equation 8. So, this is nothing but that F2 will be equal to F1 into A2 by A1. So, in this case what we can say that this device can create the large force F2 from the small force F1. This is the principle of the hydraulic press. So, here see, if we here produce a larger surface area, and then accordingly you can say what should be the force acting on this, that will be based on this small what is that force F1 here acting on this surface A1. So, this is called the principle of hydraulic press. So, this is also one important characteristics of the pressure. So, one is first one is called that the pressure of a fluid always acts, that will be perpendicular to the wall in contact with the fluid. Second one is that in the all directions the pressure will be exerting with equal value. And third one is that in this case if the fluid pressure applied to a fluid in a closed vessel, and if it is transmitted to all parts of this container at the same pressure value as that applied there. So, in this case if we apply the pressure F1 in a small cross sectional area with a small force F1, what should be the pressure is exerting there, that would be P, and that P always will be the same in this large cross sectional area, which will be resisting by this force F2. So, F2 should be some multiplication factor of this F1 which is applied in the small cross sectional area. So, this will be, if suppose A2 is the double of A1, that means here cross sectional area in this leg is double of this so we can say that the force will be required to resist this force will be double of this earlier force. Another important point, that how we can estimate the pressure whenever any fluid is acting or any fluid is exerting any pressure on the surface of the solid, and that of course you have to quantitatively express what will be the pressure there. Now, if we consider that a fluid is at rest and the pressure varies according to the depth, and then we can say here, if we consider this element of fluid here in this pond, suppose there is a fluid element like this of dz, and cross sectional area is dA in the z direction, that is the vertical direction. Then we can say that if we do the force balance over this fluid element, we can have that what should be the P at this surface here, then we can say P into dA, that will be force acting vertically upward, and it will be balanced by the force acting in this surface in the negative z direction, that will be equals to P plus dP by dz into dz. That means, here since the pressure is related to the height of the liquid column, if we consider that will be uniform pressure division along with this z, that means the pressure gradient is dP by dz, then at this dz what should be the pressure here. So, total the pressure change over this height dz, it will be dP by dz into dz. So, P plus dP by dz into dz, this will be your pressure acting over this surface here in the vertical direction, negative vertical direction. Now, here what will be the weight of this fluid, that will be dW, and it will be equals to rho z into dA into dz. dz is the height of this liquid column and cross sectional area is equal to dA. So, dA into dz is the volume, volume into rho, it is mass into z, that will be equal to force. So, this will be gravitational force. So, if we vertically balance this force, then we can say that P into dA minus P plus dP by dz into dz into dA, it will be force, and it is also force minus gravitational force, which is acting downward and vertically. So, rho into z into dA dz, that will be equals to 0. So, this is the force balance, or you can say what will be the in the positive z direction what is the force, and negative force in the negative direction, just that will be equals to equal when the fluid element will be in rest. So, in that case, from this equation number 9, we can say that dP by dz will be equals to minus rho into g. So, by this equation number 10, we can have this what will be the pressure gradient along with the height of this liquid column. So, it will be equal to simply minus rho z. Minus rho z is called the specific gravity of the fluid. So, from this, if we integrate this differential equation of this dP by dz is equal to minus rho z with this boundary condition, at z is equal to z0, P should be equal to P0. That means, at the bottom, if I consider that the P is equal to P0, then we can have after integration the constant of integration will be equal to P0 plus rho z z, and hence we can say that P will be equals to P0 plus Z0 minus Z into rho z, that will be equal to P0 plus rho z into H, because Z0 minus Z, that will be equals to what? H. So, this is your final equation, that is called equation of statics of the fluid. So, by this equation we will be able to find out what should be the pressure at a certain depth of the column. Suppose this is the pond, and here at a certain depth of H, what should be the pressure here? Simply by equation number 13 you will be able to calculate, whereas P0 here it will be equal to atmospheric pressure. So, P minus P0, that means the exact pressure minus atmospheric pressure, that is total what atmospheric pressure plus liquid height column pressure, that will be equal to rho z H. So, by this equation you will be able to find out what is the pressure at a certain depth in the pond or any water column or in a container, there you can have the pressure calculation for that. Now, in case of gas, what will happen? The density of the gas changes with pressure. So, as the altitude increases, the temperature also decreases. So, based on that, accordingly the pressure of the gas will be changing. So, based on that, P v to the power n will be equals to constant. Here n is the polytropic constant. So, in this case P v is equal to constant if this is a non-ideal gas. So, here n should be for ideal gas, it will be equal to n is equal to 1. So, P v is equal to constant. So, at z is equal to 0, at sea level you can say that P is equal to P 0 and rho is equal to rho 0. So, you can have that P by rho to the power n, that will be equal to P 0 by rho 0 to the power n. Again from equation number 10 we can we know that dP by dz that will be equal to minus rho z. So, if you substitute this equation number 16 in this equation number 10, which will be yielding that dz will be equals to minus dP by rho z. So, that will be equals to minus 1 by z into rho p 0 to the power 1 by n by rho 0 into p to the power minus 1 by n. So, into dP. So, finally, we can have after integration at z is equal to z 0, then z will be equals to this equation number 18. Now, by this equation number 18, finally, we will be having the relationship of P at a certain height based on the relative to the that means atmospheric pressure will be equals to, that is 1 minus n minus 1 by n into rho 0 g by p 0 to the into z to the power n by n minus 1. From equation 16 and 19, we can combinedly represent this equation 19 in terms of density. So, it will be density at particular height by relative density based on that density at this sea level, then it will be equals to rho z by rho 0 equals to 1 minus n minus 1 by n into rho 0 g by p 0 into z to the power 1 by n minus 1. So, by this equation number 19 and 20, you can calculate what should be the pressure at a certain height and what should be the density at a certain height by equation number 19 and 20 respectively. And pressure of gas with respect to height of atmosphere. So, now we know that when the absolute temperatures at sea level and at the point of height z are T 0 and T respectively, from equation P v is equal to R T, then we can have this P by rho R T equals to P 0 by rho 0 T 0 is equal to R. And from equation this 19 and 22, you can express that the how temperature will be changing with respect to height also. So, based on this equation number 23, you will be able to calculate the temperature change along with the height if you know the atmospheric pressure and the polytropic constant and also the density at sea level and what should be the height there. Again, from equation number 23, you can express this dT by dz what will be the temperature gradient. This will be equal to simply minus n minus 1 by n into z by r. That means, here how temperature will be decreasing whenever you are go up to a certain height from the atmosphere. The temperature decreases by 0.65 degrees centigrade every 100 meter of height in the stratosphere up to 1 kilometer high and n is equal to 1.235. So, in aeronautics it has been agreed to make the combined values of that is P 0 is equal to 101.325 kPa kilopascal and T 0 is equal to 288.15 Kelvin and rho 0, that means the density at that sea level, that will be 1.225 kg per meter cube, the standard atmospheric condition at the sea level, then temperature will be decreased by 0.65 degrees centigrade every 100 meter of high in the troposphere up to 1 kilometer where n should be considered as 1.235. So, these are the formula by which you will be able to calculate easily what will be the temperature there at a certain height, what will be the pressure at a certain height, what will be the density of the fluid at a certain height from the sea level. Again, pressure of gas with respect to height of atmosphere, you can say that if the temperature could be assumed constant over the elevation change, then we can say P v is equal to R t. So, in that case V is equal to 1 by rho, that will becomes that dP will be equals to this one becomes dP will be equals to minus P by R t g dz, or if you integrate this from P 0 to P, we can have the relationship of P is equal to P 0 into e to the power minus g z by R t. So, in this case we are considering that ideal fluid. So, that if the temperature could be assumed constant over the elevation change. Again, how to measure the pressure whenever liquid is exerting on the fluid any container surface or any solid surface by its liquid column or fluid column, then how actually you have to measure this pressure. Then there are various instruments or devices are being used to measure this pressure, like manometer and also sometimes micromanometer and some pressure gauge, and also different type of other electronic devices by which you can measure the pressure there. In this case manometer is one important equipment which is laboratory, which is used in laboratory, and you can easily measure what should be the hydrostatic pressure there. So, open end manometer is one type, and there are other types like differential manometer, sealed end manometer. Here in this diagram it is shown, this is open end, this is differential manometer, and this is sealed manometer. In the open end manometer, the difference between the fluid liquid level in each arm should be there. So, from which you will be able to calculate what should be the pressure exerted. Here in this case the difference. So, from this difference you will be able to calculate what will be the pressure by rho g into H. And again here this differential manometer to measure the pressure difference between 2 points. Here suppose here one points and another here another point. So, what will be the pressure difference between these 2 points, you can calculate by using this manometer. In the manometer generally the mercury or carbon tetrachloride fluid are being used. So, based on that difference of this arm, what is the difference of this liquid column or that is or mercury column, or if you are using carbon tetrachloride then carbon tetrachloride column, based on that you will be able to calculate rho g into H. So, rho here will be what will be the fluid. If it is mercury, then you have to consider this density of the mercury. If it is suppose carbon tetrachloride, you have to consider the density of the carbon tetrachloride here. So, by this you will be able to calculate what will be the pressure given by this fluid whenever it will be flowing through pipe like this. And here it will be the sealed end manometer. In this case here it will be near vacuum, that will be enclosed at one end, and if the open end of the sealed manometer is exposed to the atmosphere, the device functions as a barometer. Whereas, inclined manometer is also one important manometer by which you can measure the pressure. It is generally being used to modify the pressure reading, that generally if at a certain angle the manometer is being used that the pressure, the reading of that pressure will be magnified. So, this is the advantage of using this inclined manometer. And micrometer also sometimes being used when an additional gauge liquid is used in a U-tube manometer. A large difference in meniscus levels may be obtained for a very small pressure difference. So, for a very small pressure difference, sometimes it is very difficult to observe the liquid height change in the U-tube manometer. So, in that case the micro manometer it is being used. In that case the column that means here U-tube that is here tube size, sometimes it will be very small. So, in that case for small pressure differences you can have more that is differences of the height of the fluid there, and then you can calculate the additional gauge liquid pressure in that case. And other type of pressure gauge, it is called elastic type pressure gauge. That means here this elastic one here, this by this elastic behavior of this that is here, it is called one leg. So, by spring, the spring force, it will be just moving if any pressure is exerted on it. And another is electric type pressure gauge, sometimes it is called pressure transducer. So, this is electrical, by what is that, some voltage change whenever the pressure exerted in the column. So, from this voltage change, you will be able to find out how the pressure is what is the pressure inside the column. So, this is actually whenever you are going to measure this pressure, you have to calibrate this pressure transducer by known pressure. Okay. By changing that known pressure, then how the electrical device that it will change this voltage. So, you have to calibrate this pressure will change this voltage, this pressure will change this voltage. So, after plotting this, you will have one relationship between this actual pressure to this voltage change. So, from this voltage change, you will be able to calculate actual pressure whenever you will be doing any experiment or you want to measure some pressure there. Here one example to estimate the pressure. In this case, you will see if water flows downward along a pipe that is inclined at 30 degree below the horizontal as shown here in the figure, and the pressure difference P A minus P B is due partly to gravity and partly to friction. Then you have to derive what should be the algebraic equation for the pressure difference, and also evaluate the pressure difference if length is 1.52 meter and h is 15.24 centimeter. Density of the water and mercury are given here. So, what should be the pressure between these 2 points, point A and point B. So, for this you have to apply that fluid characteristics, that is principle of the fluid characteristics, that we have already obtained that equation how to measure this. We know that delta P, is equal to rho g into delta z. Okay, that means delta P by delta z will be equals to minus rho g. So, from this principle, if you are considering that there is a point here like this A, and here point 1, here point 2 and point 3, and what is that, here point 4 and then B. So, based on this, first of all what you have to do, you have to consider these 2 points A and 1. So, what should be the P A minus P 3? Sorry, if you are not considering 1, directly if we consider that 3, then you can have P A minus P 3. You can divide also P A minus P 1, then P 1 minus P 2, then P 2 minus P 3. Since in this column only water is there, so we can directly take this P 1 minus P A minus P 3, then P A minus P 3. Based on this principle, delta P that will be equals to minus rho g delta z. That means, here we can say P 1 minus P 2, that will be equal to minus rho g z 1 minus z 2. So, this is your equation, general equation. So, from this equation you can say if it is point 1 and 2, instead of 1 and 2, it will be coming A and 3. So, here P A minus P 3 will be equals to minus 1000, that is rho, this since it is water, say minus 1000 into 9.81 into what is the length here, Z 1 minus Z 2. If we consider that datum line is at the bottom of this YouTube manometer, then it will be B, like here length is given here up to this is B. So, it will be B plus 0.1524 plus A plus 1.52 into sin 30 degree, since it is inclined at 30 degree, and minus B. Similarly, P 3 minus P 4, based on this what will be the value, P 4 minus P B, what will be that, P 4 minus P b, here it is P 4 minus P b. So, after I think if we add this, we can have P a minus P b, we can have P a minus P b. So, P a minus P b will be equals to what? P a minus P b will be equals to, after summation of all those things and substituting the value of density of respective mercury and water, then you can get this 11,381.95 Newton per meter square. So, this is your final solution. Then what will be the pressure difference between A and B? So, you can easily calculate. So, this is the principle, general principle, any in any I think by any YouTube manometer you can calculate the pressure difference by this principle. You can try also this way, like find out the pressure difference of water and oil at this point 1 and 6 here. So, what will be the P 1 minus P I think 6 here. So, what will be the value here you can calculate. So, similarly, first of all you have to consider P 1 minus P 2, then it will be from this I think if you consider that this bottom line as the what is that datum line. So, you just calculate here the what is that P 1 minus first of all P 1 minus here P 1 minus P 2 and then P 2 minus P 3 then P 3 then P 3 minus P 4 and then P 4 minus P 5 and then P 5 minus P 6, what will be the value. So, in this case if you add this, finally it will come P 1 minus P 6 is equal to what. So, right hand side as per that rho into here Z 1 minus Z 2 into Z or rho Z into Z 1 minus Z 2. Similarly, here rho Z, rho here it will be water and it will be oil or mercury oil, this is oil and into Z into here it will be Z 2 minus Z 3 and this component will be 0 because Z 2 and Z 3 are same distance from the bottom, and P 3 minus P 4 it will be again P 3 minus P 4 again rho oil. So, rho oil into Z into again here P Z 3 minus Z 4 similarly like this, okay, similarly like this, then finally P 1 minus P 6, and after substitution of this you can get what will be the final value of this 10780 Pascal. Now, another example, suppose there are more than one water is used, more than one liquid is used for I think for YouTube manometer. So, they are how to calculate that pressure difference. Exactly the same way you have to consider, you have to just mark it out what should be the here that is 1, like here this will be 2, then 3, then here 4. What will be the pressure difference between P 1 and 4. So, here P 1 first you have to consider this P 1 minus P 2 and then P 2 minus P 3 and then P 3 minus P 4, and after that if you sum it up you will get that P 1 minus P 4, and respective whenever you are considering that 2 point, in that case in that leg what is the liquid is, then you have to consider the density of that particular liquid. Another important characteristics of the fluid is that is the force acting whenever there will be a dam or sluice gate is there. So, if what will be the water pressure whenever it will acting on a bank or a sluice gate. So, the total force in this diagram you see this is one dam, here this is the water body and this is the gate, and see how force is applied here, and we can see that total force due to the water pressure acting on a bank, this is bank, okay, and then acting on a bank that is built at an angle to the water surface, that is at theta. The total pressure dP here, if you consider P here, total pressure dP acting on a minute area dA here, if we consider that the total pressure acting on a minute area dA here, dA minute area considered here. So, what will be the pressure there when the centroid of A is G, centroid of A is G, its y coordinate is yg, and what is that and the depth to that is center of gravity is hg, then the total force Ft equals the product of the pressure at the centroid G and the underwater area of the bank wall. So, this is the principle by which you can calculate the total pressure acting on the total area of the bank by this fluid. So, dF will be equal to then rho g h into dA. This is the principle, that will be the pressure here, then dF by dA, that will be rho g h at a certain height h here. So, it is equal to rho g into y sin theta, as per theta you can calculate what will be the h value here, and also this F2 will be equal to then total dF, then rho g into sin theta into what is that, y is nothing but total cross sectional area will be equal to in the y direction, it will be equal to y into dA, then total F2 will be equal to rho g sin theta y g into A, that will be rho g into A g into A. Then where is the actually center of pressure? The center of pressure, it will be considered, it will be denoted by y c, that is center, exactly in which location this pressure will be exerting. The action point of P, that is pressure, that is called center of pressure C, at which a single force P produces a moment equal to the total sum of the moments around the turning axis, that is at x axis here in this case of the sluice gate produced by the total water pressure acting on all points of the gate here. So, this y c can be calculated from this y g plus I g by A y g, that will be equal to y g plus h square by 12 y g. Why this I g is nothing but, if there is a rectangular shape, then it will be I g will be equal to 1 by 12 b into h cube, and I g will be equals to pi by 64 d to the power 4. So, in this case y c, if you substitute for this rectangular shape gate, then you can calculate the y c center of the force. So, in this case I x will be equal to I g plus A into y g square, where I x is the geometrical moment of the inertia of the area for the axis, which is parallel to the x axis and passes through the centroid G, and this I x, this is I g, sorry, I g is the geometrical moment of inertia of area for the axis, which is parallel to the x axis and passes through the centroid G. So, from this force balance you will be able to calculate what will be the center of the pressure acting by this fluid on the surface of the gate. Now, what is the force to tear a cylinder? This is also important pressure characteristics that is exerted by the liquid. In that case T, if we consider that force acting per unit length of wall which tears this cylinder longitudinally, if the tensile stress due to T is lower than the allowable stress, that safety is assured there, and by utilizing this principle a thin walled pressure tank can be designed here. So, in this case if we consider that this force T is applying in this direction and pressure is acting in this direction, then at which force that you can tear this cylinder. So, in this case if we consider this T, then 2 into T into L is the length of this pipe. This is then you can get 2 T L, that will be equals to P into D L. P is the pressure and D into L is nothing but the what is that area. So, P into area, this is force, this force is will be balanced, this force will be balanced, this is the surface area, D L is the surface area, the surface area on which this pressure is acting. So, total surface is D into L. So, total force is this, whereas this direction force is acting to tear this cylinder is T. So, T will be acting on this surface is nothing but here 2 into L. So, here in this 2 T into L, 2 T to L means here T is the force per unit length, then this in the 2 surface, since this 2 over this length, this T is acting. So, in the both sides it is acting. So, that is the 2 into T L. So, then T will be equal to P D by 2. So, by this equation you will be able to calculate what should be the force to be acting, so that you will not be able to tilt this cylinder. So, the pressure should be P into D by 2, or force should be P into D by 2, and above this T you have then you will have that the cylinder is going to tear. Another problem is that if suppose if we consider the gate in figure shown here, in this case one gate like this, below to be a quarter circle of radius 80 centimeter, with the hinge 8 meter below, the water surface, if the gate is 1 meter wide, what force P is needed to hold the gate in the position shown. So, in this case total force will be equal to rho into sin theta into y g into A. So, rho into h g A as per formula discussed earlier. So, it will be total this force. Another example, if suppose a 60 centimeter gate, that is square shape, has its top edge 12 meter below, this is 12 meter below the water surface, it is on 45-degree angle, it is on 45-degree angle, and its bottom edge is hinged as shown in the figure. What momentum force per unit length is needed to just open the gate here? So, again you have to calculate what is the total force acting here, and what will be the y g, what is the y g here like this. So, y g, so y g will be equal to 17.27. What is the y c? Y c is a function of y g, then y g plus I g by A y g. So, it will be coming like this, and it will be 17.272, and then d, what is the gap between this here from this y c and this is y c, and what is the total length is like this. If you subtract this total y c from this total length, then you will be able to calculate the d value here, this gap of this at which this force is acting on the gate. So, here d will be equal to then y g plus 0.3 minus y c, it will be 0.3 meter, and in that case momentum will be equal to F t into d by L. So, it will be coming to 1940 Newton. And another important aspect that we can also calculate different aspect of what is that fluid characteristics of fluid motion. If suppose any fluid is moving with a certain acceleration, then what should be the pressure exerting on the surface by this fluid, and when suppose any fluid is moving upward or in the downward direction, or if it is flowing or if it is moving in a container at an acceleration which is equal to the gravity, then whether is there any pressure will be exerted or not, that will be discussed in the next lecture. And also other if there is an horizontal acceleration, uniform acceleration is there on the fluid, then how fluid surface will be just tilted from its original position or original surface location, and what will be the spillover of the liquid, you can also calculate. So, that will be discussed in the next lecture on this module of fluid statics. So, I think it will be helpful for you how actually pressure can be calculated. This is whenever there will be a certain liquid column at a depth, then what will be the pressure, and how the pressure force is exerted on the dam or bank of the river, that you can calculate by this module of this lecture. So, I think I should also suggest for more reading about this fluid statics by this I think textbook or any other textbook you can follow to read this content. So, thank you.